Yeah, hi guys, I'm Raghu. Uh, I'll be talking something about structural optimization and machine learning and its applications in uh, mechanism design and simulation, currently present in uh, literature. Are you all able to listen to me? Okay,
Yeah.
Yes.
sure. Okay. Uh, yeah, let me share screen then. You can. So, I mean, so are all of you guys are middle school or high school, I believe.
Yeah.
Okay, so whenever I would try to use as less jargon as possible. Whenever you don't understand a word, stop me right there. I would explain it. So I made it more with pictures than words so that you can understand better. Let's share screen now. Hmm. I believe you can see the screen. Okay. So yeah, so the two topics, these are very wide topics in themselves. Both are straight away PhD topics currently. In fact, my PhD was mostly on structural optimization. So the common thing between structural optimization and machine learning is optimization. So both of them need optimization. So I'll just briefly describe in one slide what it is. You don't need to understand the math behind it. It might be too early for you guys as of now. So optimization, do it we optimize everything in our everyday life. Suppose you are going to school by walk. uh, After 10 days after walking to school, the 10th day you would be taking a much shorter path than the first day, because slowly you have been exploring and you would always try to optimize your time taken to go to school. So I mean, that is something inadvertently we do, optimizing life. So mathematical optimization rough is fairly similar. So we have some we have a function, suppose, which looks like this, which looks like this weird cup kind of thing, and we want to find uh, the point at which this function has the minimum value. Say that's called the optimal value for this situation. So the optimization algorithms present in literature would try to find the okay, can you see my mouse pointer? Okay, let me do this thing. Yeah, it would try to find this sharp point, which uh, visually, pictorially, here we can see that that's the point at which this function has the least value. So that would be the optimum value, and the algorithms would try to find that. However, in real, I mean, not all the functions can be just plotted like this. This is a this function has two variables, x and y. That's why it can be plotted this way. But in real world, a function would be having thousands and millions of variables. For example, uh, let's take the recipe for making bread. How many different variables there are? Adding egg, the number of eggs, adding salt, amount of salt, adding yeast, amount of yeast. So all these variables, when you make them in an optimal, I mean, when you decide them in an optimal way, you get the right taste of bread. So yeah, this mathematical optimization is a very, though it's a mathematical field, it is used in all disciplines, especially in all disciplines in engineering. It's also used in economics and computer science stuff. So here we would be talking mostly about structural optimization and machine learning, right? So any doubt with this explanation? Okay, so why is it not moving? So yeah, this so optimization, how it works very briefly. So if you suppose this is a function and you are trying to find the minimum value of this function, I mean the point at which this function has the least value. So you are assuming that's called the optimum. I mean, that point is the optimum. For example, yeah, that point is called the optimum. We start from an initial solution. Say we start somewhere from here or here, as this picture shows, say from here. Then the optimization algorithms slowly try to move this point until it comes to here, and any more changes to that point from this minimum point would lead to an increase in the function value. Say you are making a dish and the dish tastes very good only when you have 2 tablespoons of salt. If you add slightly more amount or slightly less amount, the taste is bad. So that sweet spot is the thing this optimization algorithms try to achieve. So yeah, but the functions don't look like this. They are not this nice to us in real world. They are much complicated than the function which I'm showing you on the right side. It can have multiple of these minimum values. And if you see the ball example here, if we throw a ball from here, it stops at this minimum point. The optimum value. However, if you see a function like this, which have multiple of these troughs, depending on where you drop the ball from, it can land in different troughs. But as you can see from the function visually, this seems to be the most optimal point. I mean, it seems to have the least value, but unfortunately we may or may not find that value depending on where we are throwing the ball from. And the real world functions, which have more than 2 variables, x and y, cannot be plotted like this at all. So we definitely don't have any idea where to start from. So that makes this field uh, very tough sometimes. It's something like, say if you believe aliens exist on some other planets, it is theoretically possible to find that planet, but it is very improbable that we would find anytime soon. I mean, it would take years and years. I mean, try to throw different balls from different places, and maybe one of them lands in the sweet spot. I mean, best sweet spot. So when multiple of these things are present, we call it multiple optima or multiple optimum solutions.
I have a question.
Sure.
So, with the single optimum, it looks since it's in a little arc, it's more visual to see how the like the main solution. But for like in the multiple optima where it's so complex, how are you able to find the most like the best points? I guess like the sweet spots because it's just so complicated. So.
Sure. I mean, the algorithm still works in the same way. So usually we again start by throwing the ball from some initial point, and it can sometimes just be depend on luck actually, or we throw multiple of such balls. Say we throw 5 or 6 of such balls at random places, and we hope that one of them ends in the best sweet spot present. And unlike the functions which I'm showing here, which are visually representable, the real world functions cannot be represented on any computer. So even if you somehow find the best sweet spot, you don't know if that's the best sweet spot. There might be better.
Yeah.
So that's where we always tend to, I mean, if the solution is satisfactory enough, say all these points, at all these bottom points, the taste of the bread you are making with optimal ingredients tastes good. Suppose if, as you see clearly, this point seems to be better than this, but say the taste of bread is satisfactory enough here also, you would be happy and you would stop there. You would not try more. So that makes this more complicated. I'll show another picture next slide, which you would see much more complicated function than this. And there is not actually anything we can do about this. We just hope that we get good enough solution, but depending on where we throw the ball from. I mean, this we call it initial solution.
Okay.
We achieve different optimal solutions.
Okay. Thank you.
Yeah. So there is this function called Rastrigan function. I don't even want to count the number of roughs it has. It has almost 100 just based on what I see. So, I mean, if you throw a ball from here, it ends up here, and you can see that's not even close to the best bottom we can achieve. So the best bottom is somewhere here. So in such weird kind of functions, there are some algorithms called genetic algorithms, which are rough, which on a broad view, without delving into the details, I can say is that they throw multiple balls, like too many balls, and statistically they have higher chance of attaining the best solution because they are throwing too many initial solutions or balls here. So the the traditional optimization algorithms use something called gradients or sensitivities to obtain the optimum point. So for example, if I go to the previous slide, sensitivity, so just based on the word, say the ball is currently here. Say if we move the ball slightly to the left, I mean along this axis, I mean there is only one variable in this function. Y-axis is the function value, x-axis is the variable whose optimum value we want to compute here. So say we slightly disturb this position along the x-axis here. So then we can compute the function value. So if we know that moving to the ball to the left, I mean decreasing the value of w, if we know that decreasing the value of w is decreasing the value of g of w, that means we are going in the right direction, right? It is just like, I mean, you have many knobs you are tuning, and if you see that, say in the older days, radio days or TV, the older TVs, you need to turn some knobs to get good signal in the TV. So say you slightly decrease this w and you see that you are going in the right direction, that means g of w is decreasing, then you go more in that direction. And if you try to move to the if you want to increase the value of w, you can clearly see that the value of g of w increases. I mean, you can compute the value of g of w. Say this function is, say this function is the x, y is equal to x square. You can compute that function value, and you move the ball until such a point that moving to the left or moving to the right, I mean decreasing or increasing w. Someone join. Okay, so you would move the ball until such a point that both decreasing and increasing w would only lead to an increase in the function value. So the change in function value when you are slightly moving to the left or to the right is mathematically called gradient or sensitivity. Okay, so I mean you are slightly moving it to the left and to the right to see how the function value g of w is changing, and those things are called sensitivities or gradients, and traditional optimization algorithms use those values for computing. So yeah, but this genetic algorithms which I'm speaking about are used when the landscape is this bad, when there are too many optimum solutions and you want to find as many optimum solutions as possible. So they don't use gradients, they use some, yeah, okay, that would be, they don't use gradients. Let's stop there. Going deep would be very complicated. And yeah, so they don't use gradients, but they're extremely expensive and they are mostly based on guesswork. I mean, the genetic algorithms are called evolutionary algorithms. It's just like how evolution happens. Say humans, the early humans might have had a tail, and evolution slowly figured that tail is not required, so it eventually removed the tail off, right? So it's a painstakingly long process. So these algorithms, Genetic algorithms are also very painstakingly long algorithms in terms of computational time, but you might have a good chance at achieving this global, best optimum. So I only showed you the functions here, but optimization is not just that much. There is something called constraints, right? I mean, say, how would I say an example? Uh, say you want to have a good cookie recipe and you have a sweet tooth. So your objective is to maximize the sweetness of the cookie in the recipe, right? So then the optimization algorithm would just say throw infinite amount of sugar, then it would be as sweet as possible and everyone is happy. But I don't think you would want that, right? It would be something like, I should still be healthy. The amount of sugar should be such that I should be still healthy. So that's a constraint you are putting onto yourself. Say you're going to the school, trying to take the shortest path. Okay. Say your objective is to go to school in the fastest time possible. So you choose the optimization algorithm would choose the shortest path. However, you don't want you don't want the path to be dirty. Say the road should be clean there, because you need to because that's a requirement you have. So that's some constraint you should put. When you put that constraint, the optimization algorithm would give you a shortest path such that the road is neat, but also it is short. It might not be as short as when you didn't have any constraints, but it is satisfying all your constraints and giving the best possible option available. So that's how I can explain constraints in a very simple way. Uh, so they are mathematical functions too. For example, in this function, you can say the value of x and y in the optimum solution should be less than, say, a value 3 or less than a value 4. Uh, so you don't want to find, so suppose this value at this minimum value, the value of y is 1, but you don't want the value of y anywhere less than 2. So when you put that constraint, you would get somewhere here, because that's least possible, and y is equal to 2 there. I mean, it would satisfy those constraints and give you the best possible solution. So yeah, in practice, there would be a lot of constraints and lot of variables other than this x and y, and they cannot be shown in a plot, unfortunately.
I have a question.
Sure.
So, when you're talking about the examples for the constraints, like the cookies or the path to school, for these specific functions, like how are you able to determine which constraints, like how you like, cause like how do you just determine those constraints at the
Oh, those
beginning?
constraints are completely up to the one who is making the optimization problem. Just like the example I gave. So say your objective is to walk to school as fast as possible. So you set that as something called objective function. So each optimization problem has two things: objective function and constraint functions. So your objective function in this case is to go to school as fast as possible, and you are trying to you are asking the algorithm to give you the a path to school such that you take the smallest time possible. However, you have a constraint. The road should be clean, or the road should not have too many bumps, because you don't want your car to be damaged or something. I mean, whatever constraints you have. Or say you want to walk by a park in another route, so you want to go through a path which has a park beside it. So these are your requirements. You state the requirements, and the optimization algorithm will obey those requirements and try to find the best path while satisfying all your constraints or requirements, because they are like deal breakers. I need this at any cost, right?
Mhm.
And while satisfying those deal breakers, it will try to find the best answer, best solution. So that is the optimal solution while satisfying those constraints. So yeah.
Yeah. So is there like any cases when all the restraints can't be met? Like you have to
Of
do something?
course, of course, you will. I mean, there are many cases where there are. I mean, if you have, I mean, say you have this function. Say in simple case, say you have this function. You say you don't want the value of w to be less than 1. You don't want the value of w to be greater than 1. You don't want the value of w to be equal to 1. Say those three are your constraints. That means you don't want anything, right?
Yeah.
So there are, I mean, even in real life you would face such constraints many times. It's like, I mean, satisfying all those constraints, you might not find any solution at all. So that's when the optimization algorithm would give you tell you that the problem is infeasible. So the algorithms are advanced enough to tell you that the constraints are such that there is no solution available. So that's definitely possible. So since you are the one, the user is the one who decides the constraints and objective functions, they should be diligent enough to see there is at least one solution possible for the optimization algorithm to give you anything at all, right? Make sense?
Yeah, that makes sense. Yeah.
So then, like, if there's like if there's like no solutions possible, then the user will have to like remove a constraint, right?
Yeah, you have to compromise on something, right? It's like, yeah, I mean, just like in life, we can't have everything. So yeah, we have to remove some constraints. The user should remove some constraints so that there is at least one solution possible at all. Then the algorithm would try to give you the best. So we are only the users of the algorithm. It only acts based on our commands, and the commands are the instructions, the constraints and objective function we are gonna give the algorithm, right? Okay. Yeah, so when constraints are present, the optimization algorithms are a bit more, optimization is a bit more challenging area because of what I said, because there would be less number of solutions possible. So yeah, since there are less number of solutions possible, say you want to buy a cookie in a store, it should taste good and all of that, but your constraint is that it should not cost less than $3. Then don't go to insomnia cookies. That's, I mean, then the optimization algorithm would remove insomnia cookies from the feasible set. It won't give you that. The answer would not be insomnia cookies. Is that even a brand there in California? I don't know. Yeah. So yeah, something like that. So, but if you say the cost of the cookie should not be more than 50 cents, maybe there is nothing at all, right? Maybe an Oreo cookie, possibly, I don't know. Maybe there is nothing, so you won't get anything. So that's when you compromise and move the constraint a bit, saying, okay, I will spend $2, but not more. Then maybe you'll get something. Okay, so now that you have a very rough idea of what optimization is, I can speak about what structural optimization is. So structural optimization is nothing but optimization applied for the design of structures. So there are three kinds of structural optimization: sizing, shape, and topology. Uh, these are available in commercial softwares, but they're quite recent, I would say. They were not very, I mean, they have started only 6-7 years back. I mean, and Autodesk Fusion 360 has one. I checked it. It has a topology optimization. I mean, almost all the major softwares has one topology optimization. So yeah, let me briefly explain what these things are. The pictures should help possibly, but let's see. So say we want to design a bridge, okay? And this is a two-dimensional bridge. The logic applies for 3 dimensions too, right? So this is a bridge. say these two are the ends of the bridge. In civil engineering, we call this triangle a pin joint and this circular roller joint. So these two are the ends of the bridge, and this thing is the one, all these members are hanging in the air, right? So sizing optimization works something like this. So you start with many of these members, which are trusses or truss kind of members, and you would say the weight of this kind of structure is, for the purpose of discussion, 10 tons, though it would be in reality much more than that, say 10 tons. But you don't want the final solution to be optimized. You don't want the bridge to be more than 4 tons. Okay, you want it as lightweight as possible. At the same time, you don't want to compromise on safety of the people who go on the bridge. The bridge should be the bridge should not collapse under any loads which are, I mean, under any loads you are expecting. Say if 20 trucks are on the bridge, it should not collapse. However, if aeroplane smashes into the bridge, maybe it should collapse. I mean, that would be too much. Yeah, say you have some requirements on the performance of the bridge, on when it should collapse and when it shouldn't. Say you are starting with this as the initial solution. This is the initial solution you are giving to the optimizer. Each of these members, each of these bars is a variable. I mean, here, if you see, if I showed you in this plot, X and Y, there are only two variables. So you are able to plot something like this. But here, each of these bars is a variable, and I don't want to count. Maybe there are around 20 or 30. So there are 20 or 30 of these these things we call design variables in optimization. So we want to find the cross-sectional area or thickness. I mean, let's for simplicity say thickness of these bars, 20 or 30. We want to modify them such that the structure is still capable of carrying the loads like the cars on the bridge, but it should be as light in weight as possible. And you might end up getting a structure like this. So the, I mean, the darker one is the final solution. The things which are less on the background is the initial solution. If you see, you might be able to see some bridges like this in actual world. There are already some bridges like this in the real world. So what the optimizer decided is that these members are not as useful in carrying the loads when a car or a truck moves over the bridge. These members don't contribute much in terms of carrying the loads, right? So it would try to remove them first because they are not doing much anyhow, and removing them would decrease the weight of the structure here, the bridge, and your objective is to decrease the weight of the bridge, right? So in sizing optimization, so in this example mostly, the presence and absence of these members, each of these members is considered for optimization. So each of these, say there is a value 1 and 0 for each of these things. 1 means the way the member is present in the structure, 0 not present. So these ones and zeros are optimized by the optimization algorithm, and the final solution happens to be this, where these members are disappearing, so they have values like 0. These members are present, values like 1. If you see, all the horizontal members on the bottom are present because here is where the cars go, right? So there should be something. I mean, those are the members directly handling the load, right? So they are definitely present, and the loads on these members are transmitted to rest of the members. If you do some finite element analysis in some software, you would find out that actually if you try to do a finite element analysis in any software like Autodesk or Abacus on this structure with loads, like with a distributed load, I think you understand what a distributed load is, right? Just some forces on all these on this horizontal edge on the bottom where the cars and trucks go, you would actually realize that the stresses. Does everyone know what stress means? Or
Yeah, we do.
okay, sure, that's great. Yeah, I didn't know when I was in middle school, so I don't know. Yeah, so you would actually observe that these members which have disappeared would have the least stresses, and that's why they are removed by the optimization algorithm. And by these kind of algorithms, you can see that the machine, I mean the computer, is designing the structures with very less input from the user. So you don't need 100 engineers to design things anymore. You might need a couple of computers and few engineers to get the same things, because the computer is doing most of the job many engineers should be doing. So yeah, the example is the same in shape optimization and topology optimization, but the difference is that in shape optimization, we again start from an initial solution, and the initial solution looks like this. It looks with a rectangle with all filled with metal with some holes, here circles. And shape optimization just optimizes the shapes, as the name suggests. It optimizes the shapes of the surfaces, and the objective function and the goal is the same as in sizing optimization: decrease the weight, don't compromise on the structural integrity. So then it happens that the algorithm chooses something, shapes such as this in the final solution. So this is much lesser in weight, and it has very good structural integrity. And the amount of, you can add a constraint like, don't remove, the structure should be at least 3 tons, or the maximum stress at any point in this structure should not be more than XYZ megapascal. I think the units you guys use is pounds per square inch, I guess. Yeah, I mean, rest of the world uses SI units, sorry. Yeah, so you can have a constraint like, you give me the optimum, give me a lightweight structure, but the maximum stress at any point in the structure should not be more than XYZ. So that's the designer would decide those values. The algorithm would do everything in the background and just throw you the final solution, which can be then manufactured using some other techniques. Topology optimization is a layer above both sizing and shape optimization, in that here, if you start with 6 holes, right, the end product, the optimal solution, will also have 6 holes with the shapes modified. But in topology optimization, it creates its own holes. The number of holes, the shape of holes, everything is given to the computer. I mean, the computer has the most flexibility in designing the best structure possible. So you start with a initial solution like this. This rectangle is the bridge, completely filled with metal everywhere, steel. And the final solution looks like this, with the same requirements you had before, same constraints and same objective function. And this actually looks like some of the bridges present in the world currently. If you try to Google for truss bridges, a bit older bridges, they look like this actually on the side, from the side. So now the problem is that between these 3 things, sizing optimization has a very good advantage. I mean, clearly you can see that you can optimize, you are giving too much flexibility to the computer in topology optimization. So the most lightweight structures are mostly expected from topology optimization, because it is changing whatever it can, right? It is changing whatever it can. Sizing optimization and shape optimization, you are not giving that much flexibility, so they would not be that, they don't give as efficient structures as topology optimization. However, the advantage of sizing optimization is that in the market, when you are trying to buy these members, trust members, say you are buying bolts from the market, you will get say 10 bolts, 15 bolts, 25 bolts, or something like that. And sizing optimization chooses among 10, 15, 25 that way. But this topology optimization would say, give me a bolt of size 12.23 which is not present at all. So it might be impractical to use topology optimization in some scenarios. For example, you can only buy members from the market which look like this, of different cross section areas, right? So you can buy this, but if you see the members in topology optimization, they are not of uniform cross section. So the manufacturing methods are going to be different here. So that would increase the manufacturing costs. So, but however, you might have all heard of 3D printing already. So with the advent of 3D printing and additive manufacturing techniques, and it's currently going at full pace. Because of that, this field of topology optimization is currently a very great field in research, for research at least, because now I can generate a structure with optimization algorithm, which is not just existing in paper, and it can be actually manufactured and used somewhere. Though this field was in 94, started in around 94, no one cared about this field at that time because those structures were impractical, right? Yeah, I can show you some structures, some actual components printed in the next slides. So a bit better example for sizing optimization. So this is a big structure. This is the side view of the structure. This is the top view of the structure. All of those lines indicate truss members connecting 2 points. And this structure, this dome kind of structure, is loaded at this top point. It is pressed from the top. And the goal is again the same: give me as lightweight structure as possible, and don't compromise on structural integrity by having constraints on stress, etc. So here the design variables, I mean, what we are asking the optimizer to modify or change are the, so if you see, there are some numbers on this picture. Those numbers indicate that all of those members are of the same type. I mean, they look like the same even after, they look the same even after optimization. So they are like one class of members. So you are trying to optimize for the cross-sectional areas of each of these class of members. So in this problem, there are around, I can't see the number from him, there are around 20 odd different kinds of members. So you are trying to optimize for 20 cross-sectional areas using the optimization algorithm. 20 is not a big number, but however, you can't see a 20-dimensional function on your laptop or anywhere else. So from the visualization point of view, you can't see the function. From the optimization of point of view, 20 is not that big a number. And for a sizing, so this is the optimal structure. The original structure, I'm sorry. So this is the original structure and the optimized structure. What you are optimizing for is the cross-sectional area of each of these members. Say these members initially were 50-inch square. The optimum solution might say they should be 25-inch square. Say these members were 50-inch square initially in the initial solution. The optimizer might think that, might judge that since they are near the support points, they should be strong enough, and might increase the cross-section area of these members to say 16 square. So sizing optimization is relatively the most simplest optimization. You would be mostly optimizing for things like radii, lengths of different kinds of members, or the angles between different members. There are typically like tens and hundreds of parameters. It also supports discrete variables. What I mean by discrete variables is that, say you are trying to find the optimum bolt which goes into your structure. When you go to the market, you can only buy bolts of 10 15 25 20 something like that. Maybe you cannot buy 12.21 So sizing optimization can prudently pick among those discrete values and give you the best possible solution. So, and these structures are typically very easy to manufacture because they are not complicated structures. We are just changing the cross-sectional areas. For example, in this algorithm, you can manufacture using conventional techniques of manufacturing. Like there are some techniques like lathe and machine. I'm not sure you are familiar with that. Let me not go there. So yeah, this is a bit deeper explanation of sizing optimization. So shape optimization, the basic thing I explained you before for shape optimization a couple of slides back still holds. You're just gonna, the optimization algorithm is just gonna modify the shapes of surfaces such that the weight or such that the component is light in weight, however does not lose structural integrity. See, this thing is like a wrench. I mean, in 2 dimensions, this is like a wrench. I think you know what a wrench is. You can tighten nuts with that. Say this thing is 2 kilograms currently, the initial solution. You want to optimize this shape, this slot in between, and these edges here, such that you have weight loss, but you want structural integrity. That means when you are tightening a nut, you don't want the wrench to break. So you would put those constraints, and you get the optimization algorithm would modify this shape and the outside shapes to be something like this. Clearly, visually, this thing is much lighter in weight than the original solution. However, it can achieve all the things the initial solution can achieve. Sorry, let me take that back. It can achieve, there is still very good structural integrity as per your needs. Say the torque with which you want to rotate, say the torque say the maximum stress you are expecting on this wrench is some 50 megapascal. For 50 megapascal, this solution would work great, and you should make sure that you would not use this wrench for applications where there would be more stresses than 50 megapascal. Then it would break, right? Because you didn't inform the optimizer that you are going to forcing stresses of more than 50 megapascal. So the contours, the colors on these pictures are the stress value, indicate the stresses. If you see, the initial solution has very less stresses as compared to the final solution. However, you should make sure when specifying the constraints that this maximum stress which is happening here is still within agreeable limits, which is chosen completely by you based on the application you're going to use this wrench for. So however, here you should notice that you should add another, you should choose something called design domains. So here you are choosing to optimize for this shape, this slot shape, and the outer cross-section shape. However, you are not optimizing for this shape or this shape. Why? Because this is where you are gonna place the nut, right? I mean, if you optimize for this shape, what are you putting? I mean, you can't compromise on this circle ever, because you're gonna place the nut there while wrenching. So this surface and this surface and this slot surface are called designable variables, designable surfaces, and the shape optimization algorithm would give you some optimized surfaces. So this is another example. It's a bracket which holds moving parts. Say there is a part here, some part in a car or somewhere else. There is a part here, there is a part here, there is a part here, and you have bolted down in these 3 circular locations, right? And there would be some stresses in this bracket, but you want this to be lightweight again, albeit acceptable stresses, within acceptable stresses. Then the shape optimize, you want to optimize for this shape here. However, you don't want to optimize for these 3 shapes because you are going to put bolts there. You don't want to change those shapes. You are going to change this shape and these 2 shapes. If you see, you get this bracket, and visibly it is much lighter in weight, but though it looks flimsy, based on the numbers, based on the constraints you are providing to the optimizer, say you are not using this bracket in a high stake situation. Say you know that there are not going to be too much stresses on this bracket. So it doesn't need all that material. It can shed off all that material and it is just this. So this kind of optimization has more design variables than sizing optimization, typically hundreds or 100,000s. So it takes much more time than sizing optimization in terms of computing. The computer takes more time, and there are still the conventional techniques of manufacturing can be used to manufacture these two parts, but these parts are not directly, you can't go directly to the market and buy them. For example, in sizing optimization, if you use discrete variables, say if the optimization algorithm says use a 15 bolt, directly go to the market and you can buy it. But here you should do some machining to obtain this part or this part. Now topology optimization, as I said, it has the most flexibility. It puts holes and distributes the holes at different parts of the structure and optimizes for their shapes. Suppose you have an initial, this is a bracket again holding two different parts using bolts here. Say you want it to be lightweight again without compromising structural integrity. Now you are using topology optimization to optimize it to the extreme to make it as lightweight as possible. So say you don't want this initial solution is 1 kilogram. You don't want the final solution, optimum solution, to be less than 3/4 of a kilogram. You might end up with this. Half kilogram, you end up with this. 1/4 of a kilogram, you end up with this. You can see that this is a pretty complicated structure, and most likely you have never seen such bracket in the market. In the market, you would see mostly this thing, because these things are not manufacturable using any conventional techniques. You need to use 3D printing for this, and that's why these kind of things you would be seeing in high stake situations. For example, a very good application for these kind of things, consider an aeroplane. Even 10 kilograms loss of an even if you are able to decrease the weight of the aeroplane by 10 kilograms, you are going to save many gallons of fuel, which is a very great advantage. The same with space structures. Say you are having you are sending a satellite to moon with some fuel. Say you are able to decrease the weight of the satellite using such optimization, topology optimization algorithm, by say 50 kilograms without compromising on anything. Since it is a space kind of structure, you have enough money to do additive manufacturing. So now you can save so much on fuel that instead with the same amount of fuel with which you are going to moon, you can end up going to Mars. So it has tremendous applications in such kind of situations. So this is another example. It is a brake pedal or an acceleration pedal from a car. This happens to be the initial solution. These two holes are the hinges. When you press the brake pedal in a car, these two are the mount points of the brake pedal, so you should not optimize those points. You want these to be lightweight too, so that you can press the pedal as fast as possible. And you can see the final solution. This is the final solution from the optimization. You can see that it has some ragged edges, it has some jagged edges. So from those jagged edges, the engineer or whoever the user is should construct a neater looking part like this, so that they can use additive manufacturing to manufacture. For example, these parts are actually additive manufactured, taken from a website straight away. The number of parameters, if shape optimization is worse, this is almost impossible. Sometimes it can have even 1 billion parameters. I mean, I saw one work which has 1 billion parameters. So the optimization takes for days sometimes. And as I showed you in the initial slides, the multiple optimum situation, the final solution might not even be great sometimes, because there are just too many optimum points, and you ended up in a very bad optimum point because your initial solution is something like that. So that's what makes this field a bit challenging, uh, because of the high computational resources, one of the things, and manufacturability. Yeah, you should make sure that the product which you are obtaining by the optimization algorithm is actually manufacturable. Otherwise, it is kind of useless, right? Any questions on these 3 slides? Okay. So, okay, in a very simple way for topology optimization, a very simple algorithm, what it does is, it's a 2-dimensional structure here. In civil engineering and mechanical engineering, it's called a cantilever beam. You might actually notice such a structure in your homes. If you have a TV hanging by the wall, the things which are connecting the TV to the wall are called cantilever supports. So this thing is the wall. This thing is a load. As in the TV example, this can be the load of the TV. So you want to optimize this mount, this cantilever structure, which is fixed to the wall when there is a load drawing this down, so that it has less weight. Then so the process is that first we do a simulation, stress analysis, static stress analysis kind of thing, by methods like finite element method, or many other methods. Let's just say static stress analysis for now. I believe some or most of you guys know it. So once we do the static stress analysis, since our objective is to decrease the weight of the structure while still maintaining structural integrity, our obvious choice would be removing the areas in the structure which don't have high stresses. If they don't have high stresses, that means they are not contributing so much in carrying the load of your TV. So if that happens for this example to be this area and this area and this area, when the loads are this way. If the loads are any other different direction, this might not be the case. Only when the loads are this way, it happens that this area and this area and this area are not much useful in carrying the loads. They have low stresses. So the optimization algorithm diligently removes those areas, and it happens over multiple iterations. It slowly removes them until it achieves the required objective. Until it achieves the required objective while satisfying the constraints you have. So it happens this way. It starts this way, and slowly it removes more and more material, and it ends up with this kind of structure, which is the most optimal structure, which has the structural integrity you desired, and it has as least weight as possible. So this thing is like 40% of the weight of the initial structure. Though no one optimizes for things like TV mounts and stuff, this is an educational example. I mean, if the algorithm works here, the same algorithm is used in space structures. There is nothing different. So this part can be manufactured using additive manufacturing, 3D printing, many such things. I mean, sometimes conventional methods of manufacturing are also possible. So this is roughly how topology optimization works. So we compute the stresses, and I said sensitivities in the first slide, right? We slowly push the ball. We slowly change the value of W. See, let's go back a bit. So we slowly change the value of W to the left and right, and see which direction J of W is actually decreasing. Since if we move to the left and then compute J of W, the value of J of W decreases. We slowly move it until here. It is just the same, except that there is not one W here. There are like a million W's here. So you can completely expect that you cannot do this by hand. You always need a computer for this. For that W thing, you can always do it by hand. For this thing, you can never do it by hand. I mean, you should be very patient to do it for 1 million variables. So yeah, whatever I said verbally before, it is just this thing. So initially, so the question you asked before, the user, the engineer or the user decides on the objective function and constraint functions. So here the objective function, this is called mean strain energy. Let's ignore what it means, unless you already know what it is. So it is the energy stored in different areas of the structure. It kind of defines how much so how say if I assign a number 5 here and 2 here, that means this portion of the structure handles loads more than this area. So this area is not contributing so much in terms of handling loads, so we remove that. So those numbers represent mean strain energy or the energy stored in the structure. So first we define the model, like loads here, boundary conditions, the design domain, which means this complete rectangle which is to be optimized. You define those, and the material properties, steel, aluminum, plastic, anything. And then you decide the objective function and all your constraints, like maximum stress in this structure should be so and so, etc. Then you analyze the model using techniques like finite element method, and there are many other methods. For structures, it is just static stress analysis. Let's just say static stress analysis. There are many other kind of analysis like dynamic analysis, etc. Let's just stick with static stress analysis for example. Then we compute these things called sensitivities, which I said before. When we move the ball a bit to the left, the change in value of the function is called the sensitivity. Except that now there is not one ball, there are a million balls. So by moving all those balls, we try to compute the change in the values of the objective and constraint functions. So those are the gradients or the sensitivities. They are not applicable in some other algorithms like genetic algorithms. They are gradient free methods. Now, based on this sensitivity information, the optimizer decides whether to remove the material from those portions if they are not contributing much, or add some material to those places if it is not contributing as much. So that's called updating the design variables. And this process is continued on and on until no notable changes in the structure is observed. For example, if you see there are some changes from here to here, some changes here to here, here to here, there are some changes, here to here, some changes. From here to here, there is very less changes. That's when we call the optimization algorithm has achieved convergence. I mean, it is not changing the solutions anymore, so stop there. So, okay, this is one more interesting thing which is happening from the last 3-4 years. It is something called lattice structures to make it much more lightweight, and this is completely because of additive manufacturing. I showed you this bracket before, right? So this bracket, instead of having the bracket itself, they fill it with something called lattice. These small minute structures which are repeated on and on. These things can only be made by additive manufacturing and not any conventional techniques. So this thing is going, since as you see this is very porous, so this is definitely going to be much lighter in weight. So we optimize this lattice shape such that the structural integrity of the overall structure is still maintained, but it is very light in weight. So these kind of structures, the example I gave, like aircrafts or space structures, it is extremely beneficial there, but still so futuristic. They still don't want to mess with the existing airplanes. Don't worry, they didn't put these components in your airplane. Not yet, maybe soon, who knows. So Autodesk does have a product called Lattice Commander to put these lattice structures inside any component you have. However, you should be able to manufacture that only using additive manufacturing. So with this, I'm finishing on structural optimization. Let me stop there and ask you if you have any questions. Anywhere, it's fine. Okay. Yeah, I hope I didn't use any jargon. I'm just thinking. Yeah. So machine learning, this is again a grad school topic. So I try to use more pictures than words to explain it in the simplest way possible. So I guess everyone knows what a function means, because I already spoke the word function too many times. So you know that what a word function means. So suppose you have a function y is equal to f of x. Say call x as the input, y as the output. You have outputs and inputs. Have you guys used Microsoft Excel where you do something called list square fitting? Did you do such thing before? Not, it's fine. Say you have some inputs, say you have some outputs. You fit, you are given some outputs, you are, and with associated inputs, you want to compute the function f, which is linking these two things. That basically is entire field of machine learning. I mean, putting it this way makes it so simple, but it is not as simple as said, because the number of inputs and outputs is going to be too many. Simple example, say the simple example is handwriting recognition. Say you write numbers 1, 2, 3, 4, 5, and so on till 9, and you take pictures of all of them. You know that our phones are currently able to understand our handwriting. There are many softwares for that. They use machine learning on the background. How? They make an algorithm. The machine learning algorithms are given many inputs and associated outputs. So when I teach a child, say there is a child, say suppose there is a child, I want to teach numbers. I would write this and say this is 1. I don't know if you can see it. I would write 1 and say it's 1. So I would write, and some people also write 1 this way with some things on the top and bottom, and I show the kid that's 1. And eventually in the future, when the kid goes on to read numbers by himself or herself, when he finds a 1, he detects that 1, and whatever thinking is going on in his brain, I mean, even if the 1 does not exactly look like this one or this one, if it looks roughly same, he detects, the kid is gonna detect that 1. How? Because his brain has learned how a 1 looks like as compared to other numbers. So 1, 2, 3, we write all those numbers and train the kid, right, to say how the numbers might look like. I mean, even in the future, if the kid looks at those numbers, even if they don't look like the same, the kid is still gonna guess based on the similarity of shapes, right? So the thing which is constructed in his brain, we want the computer to do that instead of the kid. We train, so the inputs here are the images for the handwriting recognition. We are going to give the computer many images of 1s, 2s, 3s, so on until 9. Say you are giving some 50,000 or 100,000 images. And since the data is given by you, you already know this is a 1 and this is a 1. You will tell the computer, so the X is the images you are giving, the Y is the labels, 1, 2, you are giving those numbers. So the computer uses machine learning algorithms to figure out this function f. So whenever in the future you give, I write another 1 and show it, it tries to look at the closest shape and try to guess which one it is, if it is 1 or 2 or 3. And that simply is a very simple example of machine learning, right? So for example, here there are two kinds of machine learning, supervised and unsupervised. The example I gave you for handwriting recognition is supervised learning. Say for example, you have many images of duck, sorry, you have many images of birds, and you want the machine learning algorithm to know if it is a duck or if it is not a duck, right? You would supply it with enormous amount of data with many images telling that this is a duck, sorry, telling that this is a duck, this is not a duck, this rabbit is not a duck, this shark is not a duck, right? And then in the future, when you click a picture, say this thing, you can actually, you already have this in your phones. When you click a picture, okay, I don't know if you guys use, I use Android, maybe I don't know how Apple works. So when you click a picture, if you ask the phone to guess what it is going to guess what it is. If you click a picture of duck in the future somewhere in the wild, it would say it's a duck because it is already trained with all these things, right? So it is just a, I mean, instead of a human learning, just like a human learns based on his experiences or her experiences, the computer is going to learn based on the data we are going to provide. So what supervised learning is that we give images and we are also saying it's a duck and not a duck. So these things are called labels. Duck, not a duck, are called labels. So when those labels are given, it's supervised learning. In unsupervised learning, we just give images and we ask the algorithm tries to sort these images such that try to cluster them. For example, say I have a basket of mangoes and apples and I give it to a kid, very young kid who doesn't know what an apple is, what a mango is. I mean, the kid does not know the names of these fruits, right? We ask the kid to sort them according to how they look like, right? The kid is most likely going to sort based on how they look like. If apples all look closely alike as compared to mangoes, unless someone makes a mango who looks like an apple, the kid is most likely gonna sort all the apples on one side and mangoes on one side. That thing is called clustering, and that thing is called unsupervised learning because we didn't tell the kid that this fruit is apple, this fruit is mango, now give me all the apples, right? So this same task is done by the computer, and it's called and that's why it's called machine learning instead of a human learning. Here a human learns based on their experiences, here the machine is learning based on the data we are giving, right? uh, did you understand the fundamental thing here? Okay, please feel free to stop me anywhere, okay? So yeah, and you might have heard of these words machine learning and deep learning already. I'll tell you where these things are very there is only one small difference between these two, right? Say the difference is something called feature extraction. What it means, say again, let's take the same example of a basket of apples and mangoes. Say I ask you guys, figure out what all features we can use to distinguish between fruits. Can anyone say anything? What can we use in fruits to distinguish one from the other?
Well, I guess
Size.
one thing is
Color.
Yeah, exactly. So color,
texture.
sweetness,
Size.
size. Yeah, I mean, we all inadvertently, all the humans, I mean, when we were kids, we learned one fruit different from the other based on its taste. I mean, even today when we find a new fruit, I mean, if you show me a fruit which I have never eaten, for example, I ate dragon fruit only last year. If you ask me how a dragon fruit was before that, I had no idea, right? I mean, I only know from the images I saw on the internet. So those are the features. So these features are to be given by the user, and you should be assigning the value for. So you give the input data to the computer, right? Instead of giving the image of apple, here you are going to say I have a fruit which has a sweetness of 10, say we have a rating of 0 to 10. Okay, we have a fruit of sweetness 10. It looks yellow. It looks, it has a big seed inside. Do you want to guess what the fruit is?
Mango.
Yeah, that's what the machine learning algorithm would do. Simply saying, whatever you did in your mind, the algorithm would do for you. So that is called feature extraction. Here I'm saying sweetness, seed size, color, etc. Right? For not for all the for many applications, this kind of feature extraction by a person is not possible, because there are like thousands and thousands of features possible for something. Say in autonomous driving, when you want a car to drive by itself, there are not many features we are gonna, I mean, okay, that would be a very complicated example to relate here. Say an X-ray, a chest X-ray. During COVID, this happened, that there are many research papers out there. When you give the chest X-ray to the machine learning algorithm, it would tell you if you have COVID or not. So the advantage of this process is that once you have a chest X-ray, the actual system in US is that the X-ray goes to a radiologist, and that person takes significant amount of time to investigate and then tell you. So you might get the test result in 2 days after X-ray. Now, once you have the X-ray, the machine learning algorithm in fraction of second tells you yes or no. And the accuracy of machine learning algorithms in some applications, like the chest X-ray application, is almost the same as doctors, radiologists' prediction currently. Not in all applications, but at least in that application. So now, if I ask you, find the features in a chest X-ray, I don't think any of us know. First of all, we are not from that field, and it is not easy for the people in that field also to recognize the features. I mean, it is not like a color or a shape or a size. There is no such simple features. So that's where we use something called deep learning. So you might have seen this picture before. I won't explain you what this picture is. It's just called something called a neural network. It is named so because it tries to mimic what happens in the neurons in the brain. The learning, when you have experiences, the input, output, I mean, based on the input and the output, you already know. For example, I showed you 10 pictures of mangoes, 10 different pictures of mangoes, and told you that it's a mango. The 11th picture, you would guess it is a mango. I mean, as long as it looks close enough to any of those pictures. So this network is going to learn that. Say if you input to this network a picture of a mango without any features, like the thing I was saying, the sweetness, you don't give anything, just give the image, right? It is going to guess, yes, it's a mango or pomegranate, etc. So this neural network is what f here is. Y is equal to f of x. X is the picture of mango. Y is the answer if it's a mango or pomegranate, etc., etc. This f is what they call neural network. So each of these links, edges here, are supposed to mimic the neurons in our brains. They are no way close to replicating our. I mean, you should be happy. They are not going to take over the world anytime soon. At least not in my lifetime. I hope so. So they are called neurons, and their intention is to mimic the human neurons by learning based on the inputs and outputs. And how they learn is that there is an optimization involved in this neural network, and that's why I said optimization is the common thing between both structural optimization and machine learning. Yeah, so though I gave the example of mango and apple, this slide has car and not car. I think you understand the resemblance. Yeah, tire size, etc. Yeah. So that's a very, very broad, I mean, very, very, very high overview of what deep learning is. I mean, this field is so fast growing that each day there are 2-3 papers coming out. I mean, 2-3, I might be kidding, there might be 10 papers coming out. And this field is so fast paced that the courses I took 2 years back are already redundant or already useless because the field has changed already. I mean, there are just too many researchers working on this thing. I mean, the Tesla autonomous cars, etc., are all based on this machine and deep learning. Okay, talking of Tesla autonomous cars, there is this thing called reinforcement learning, which uses deep learning again, but it is used to control the actions of a robot. For the simple case is a robot. Assume you have a robot. Okay, to explain reinforcement learning, I don't think you guys watch Big Bang Theory, but let's ignore that example.
I do.
Yeah.
I've seen some.
Yeah, I guess Sheldon teaches Penny by reinforcement, right? By giving chocolate or something. This is exactly that. This is exactly that. I mean, a similar example. Let me talk about similar example. You have a monkey in a cage, and you have there are few buttons beside the monkey. There are 2 buttons. One is green, one is red. Whenever the monkey gives hits on the green button, you would give it a banana. When it hits the red button, you throw water on its face. Okay. Now slowly you would change the experiment by moving the buttons at different. You will still have the same color, but you will change at different portions in the places in the cage. And again, whenever the monkey hits the red button, you'll throw water on its face. Green button, give a banana. And eventually the monkey figures out that regardless of where the green button is, I should hit on it. Okay. That's called reinforcement learning. I mean, instead of the monkey's brain, it's the computer's brain or the robot's brain. I mean, that might be called robots thinking. Yeah. So suppose you have a robot. Let's take a very simple example of a robot, right? Say Pac-Man. It's an old game, I know that, but I think you have seen Pac-Man, most of you guys.
Yeah.
So in Pac-Man, say the hero is a robot, or in reinforcement learning language, it is an agent. It is called agent. So Pac-Man, say we randomly run some experiments by making the Pac-Man going in random directions based randomly, whatever the randomization algorithm decides. And whenever it eats the Pac-Man eats food, we give it a reward, like the banana. I mean, since this is a mathematical algorithm, we assign a number like +1, +2, something like that. And whenever it hits the Pac-Man hits a ghost, we would give a negative reward, -3, -4, just like throwing water on the monkey's face, right? Based on, so we run many of such experiments, and finally the Pac-Man, we will just, after so much of data, there is some optimization we conduct. Afterwards, this policy is something which is like the virtual mind of the robot. I mean, it's a cloud. Imagine it's the mind of the robot. After all these data points, after all these experiences, Pac-Man will learn that eating the food is higher reward, and Pac-Man wants higher reward. So it will only, the Pac-Man would move such that it Pac-Man can eat as much food as possible while not hitting any ghosts, right? Because it accounts for negative reward. So the thing, the path which the Pac-Man takes is called policy in reinforcement learning language. I mean, for the purpose of our discussion, it's just the way the robot thinks. Now replace Pac-Man with actual robot in a room, say in a maze. There is a robot in a maze, and it should not bump into any walls. It should only say there is a maze, and okay, yeah, this looks like a maze, luckily, so I don't need to show my hands. So say the robot is entering here, and say it should exit from here. Okay, it should not bump into any of these walls. So we conduct some experiments, random experiments with the robots. Whenever the robot hits the wall, we assign a negative reward. Whenever as the robot comes closer to the target point, we assign a positive reward. We keep on going, assigning positive reward. So the robot, and we conduct some optimization. After that, the robot learns a policy that, oh, if I go more towards the target, the robot does not even know that there is something called target. The robot is only greedy for rewards. Okay. So to maximize its reward, it would frame a policy such that it goes towards the target so that it can maximize its reward. And we already added experiences in the virtual mind of the robot that whenever it hits the wall, it will get a negative reward. So it would try not hitting the wall as much as possible. It might hit once or twice, but not much. So you might have seen videos on Facebook about Boston Dynamics, maybe.
Yeah.
Yeah, that pretty much is reinforcement learning. This environment is something which is very important, because unlike machine, the environment is that, if you see that Boston Dynamics videos, the dog robot, whenever it is walking, say it has a target point to move to. When it is moving, the engineers would be kicking it. Okay, even if the robot is kicked, it falls down and then gets up and moves towards the target. That kicking in is the changes in the environment. So regardless of the changes in the environment, say in an autonomous driving car, in a self-driving car, say you want to turn the wheel by 20 degrees to the left. Okay, you try to turn the steering, say the robot, there is no driver, say the wheel is turned the steering wheel is turned so that the wheels turn by 20 degrees, but it doesn't happen like that. Maybe the road has some bumps on it, so 20 degrees rotation is not possible. It only moves by, say, 15 degrees, right? That thing is unknown because the environment is always changing, because the road is always changing for a self-driving car. So even when that happens, it would still make sure that its policy is such that rewards are always increased. So this policy is something dynamic. It is not static. If you change the environment, say when you train a Tesla driving car, yes, if it should run both in California's roads and Colorado's roads, where the roads might be not as good, right? So the policy is dynamic. Even say you have point A to point B in California, you want the autonomous car to travel, right? And it travels. You learn that policy. The next day there is a lot of traffic. It should, the way the car should drive changes, right? So the policy is something dynamic, and the presence of these cars on the road, cars, etc., constitutes the environment for the robot. In the case of self-driving car, the car itself is the robot, and the instructions which goes into the virtual mind of the car, go left, go at this pace, apply brakes, constitutes this policy.
I have a
So yeah,
question. So how do you use deep learning on this reinforcement learning? Since
okay.
since I don't think you can do gradients because it's
No, we can do that. If I write those equations, you might not understand, so I didn't write that. But what happens is that, so if you see, we still have input and output here, right? So when we do some experimental runs before with the car, so say the robot hitting the walls, whenever it hit the wall, we gave a negative reward. Whenever it moved close to the target, we gave a positive reward, right? This thing constitutes the data, right? Now this data is fed into a neural network, which that neural network tries to decide the action this agent needs to take or the robot needs to take. And that action should be such that my future reward, my final reward, should be the maximum possible, right? the robot should reach the target in the best way possible by not hitting any walls, right? So it tries to achieve that goal. It tries to take actions such that the value of the final reward, is as high as possible. And this neural network is going to choose those actions. And the series of those actions, all those actions combined together, is called the policy, right?
But doesn't the data change each time the agent learns, since you're not fitting it to something?
We are not fitting. It's like, okay, if I should go a bit deeper. So should I? So there is something called state. So in Pac-Man, say there is Pac-Man here, and there is a food pellet here, and there is a ghost here, right?
Yeah.
The neural network in the previous experimental runs knows that going towards the pellet is more beneficial because it gives more reward from the experimental runs. But if it goes towards the ghost, it knows that from experiences learned through the neural network and data we provided earlier, it would get a negative reward. So it turns to go towards the pellet. Now the environment changes. Say the ghost is here, the food pellet is here, Pac-Man is here. What does it do? The only experience it has is that go towards the food pellet and not towards the ghost. It will change direction towards this. So the policy is changed according to the environment and the state. So the state of Pac-Man, the game of Pac-Man, is such that there is a ghost here. In this current instance, the ghost is here and the food pellet is here. At some other instance, the ghost is here and the pellet is here and Pac-Man is here. So it always, so the policy is such that the policy is learned by the neural network from the experiences, the data we gave earlier. And it also learns on the flow. So suppose it hits a ghost in the future, that data point is also collected and saved, and that is used to, for example, how would I describe this? Say, I don't think you guys cook, any of you guys, but say you guys are baking something, right? No, let's not do baking. Let's do, you are cooking something, okay? And you are trying to fry something, and the heat is on medium, and you slowly observe that it is burning, the veggies are burning, and you know from your experiences that veggies burning is not a good thing. So your policy, the mind makes a policy that decrease the heat, right? Now you go to your neighbors, so from medium you turn it to say somewhere between medium and low, so halfway between medium and low. So say that's your policy, right? In the future, when you again cook those veggies in the same range, in the same stove, you would starting in between. If you have the same veggies, say you are cooking cucumber, again you start by putting the stove between low and medium, halfway between. Now you go to your friend's home and again start cooking. Your friend's stove is completely different, but you still start with halfway between medium and low. The thing again gets burnt, the cucumbers again get burnt. So now your policy should be changing, right? You would change such, you would again decrease it. So the thinking is constant. It is not the answer which you are learning here. So the halfway between medium and low, it is not a constant. It changes on the stove. The stove is the environment. So you will always change it. Even if you are not successful, you might not be successful always. You might crash sometimes. The robot might crash sometimes. Suppose if the robot is trained in this maze and I take it to another maze, it might bump into it a couple of times, but it knows that never crash into walls. It is not a good thing, right? And always go towards the direction where the reward is, where you are getting more reward, right? Say in this maze, if you are assigning more and more reward to the robot as it is going up and up, say there is another maze which looks differently than this, but you are assigning, but the target is here and you are assigning more and more reward as the robot reaches to the left. Then the robot doesn't go there. The robot goes here. What it is learning is it is greedy for reward. That's it. So that's the only thing we are teaching the robot. That's the policy.
All right.
So the data points are going to the experiences it is collecting, the robot, go through a neural network and tell the robot that take an action such that rewards are maximum. That's it. There is no final answer like car and not car, mango or apple. There is no such thing because this is a dynamic environment, and this is something where you guys can design robots. Say you have a rigid body mechanism. You know that you can put motors into the rigid body mechanism to, I mean, the mechanism itself can act as a robot based on the way you control the motor, right? Say, I don't know if you know the wiper mechanism and stuff. Oh, okay. Say you have a 4-bar mechanism, 4 links, right? And you have a pencil at one corner and you have a motor at another corner. You need to, you want to write a P, an alphabet P with the pencil there on a piece of paper by turning the motor, right? You can use reinforcement learning for this purpose. So you can, I will show you an example work which is already done. However, I mean, how it is. Yes, please.
I have to leave the meeting a little early, but
Oh, did I just go so much over time? Yeah, I went over time. Sorry.
yeah, thank you for the presentation.
That's fine. Yeah.
I'll just leave now.
Sure. Yeah.
Okay.
The next slides are just gonna be pictures of what I said before. It's not gonna be anything different.
Okay. Yeah. Bye. Thank you.
Bye. Did that partially answer your question? I don't know.
Yeah.
This field is too new. Actually, this field only gained popularity from 2017 or so. Whatever I learned last year is already useless in this field. But of course, this picture still holds true. And how it is done, the neural networks which are used here change every other month. So unless you are a researcher in this field, you wouldn't know what to do there. And it is not in any commercial software because it is this new field.
Oh, right. I have to go to.
Okay, sure. Bye.
Okay, yeah, bye. Thank you.
So yeah, this is an example of a controller. Here we are trying to control. So this is a, have you ever tried to balance a stick on your hand? So here we are asking here the objective function, we are providing more rewards to the robot if it can have this pole vertically as possible. We are going to give it more reward. If it falls down, it gets negative reward, and it can only move horizontally back and forth to achieve that. And as you know, if you have ever tried this, it is almost a very difficult task. We are bound to fail sometime. So we are trying, this is like a game. This is like a game we are designing here. So it uses reinforcement learning to decide the policy, whether to move back and forth at any instance of time. And there might be air blowing from any side randomly, right? Suppose when it is here, the air blows randomly and it tries to fall to that side. Then the robot, the robot here is just this controller. It tries to move more towards the left so that this pole still remains in the air and you get more reward. So that's like a very small example. It is practically useless in real life, but it is a very good example to show you we can do. This is a similar example where a toy car learns by itself how to travel on the road, and we have only one camera, which is, we have one camera which is observing the path the car is going to take, and the camera input is going to decide the policy of the car, whether to go to the left or right, should it turn or no. And yeah, all this learning using this data always uses neural networks. DL stands for deep learning, and we always want to maximize the rewards. So yeah, that's one example. So this is an example where neural networks are used to predict rigid body motions. Again, this is not in any software. This is right off from a research paper. How it is done is just too advanced, including for me. I would need a week to understand how it is done myself. So how it works is that their application is that they have an image of an object and a ball, and this arrow is an input vector they are giving. If the ball moves in that direction and hits the object, this cube here, how is it gonna move? And the neural network would predict an image, would predict an output image, which predicts the motion, the rigid body motion of this object when the ball is hit in the specified direction in the arrow. So a lot of data is given to the neural network for training to predict this thing. You didn't, as you see, you can definitely predict this by hand by writing some rigid body equations. But as you see, you did nothing of that sort here. The neural network is deciding, predicting everything based on the data it has learned. Not always it can do correctly, it can do sometimes wrong. It is only as good, the algorithm might not be as perfect, it can only be 95% accurate, and it completely depends on the data. So this is, this is the ground truth, which means when a ball actually hits in that direction on this object, it moves this way. And these are the predictions of the neural networks. They have some, this column is the neural network the authors made, the others are from the existing literature. They want to brag that they are better than them. So this is an application they have. So rigid body motion can definitely be predicted by a neural network. And if you are actually interested in using that, they have a GitHub code for that, and you should use that. It is not that simple as said. Yeah, it's a very complicated field. Input image, we give this as the output image as the data, and if for it, when we actually just give this image, it predicts this thing, right? The data actually consists of some things like this: inputs, outputs, inputs, outputs, and it can predict on the future images where we are giving some directions. So we can predict rigid body motions pretty simply using this kind of neural networks for complicated applications. The training, this optimization is called training in machine learning field. This can take days, actually months sometimes, and it requires heavy computational power. Like there are thousands of computers parallelly operating to learn this policy, learn this neural network to learn the rigid body motion. This is a similar example. This is a billiards table where this is the cue ball, and we are asking the machine. We train the machine learning we train the neural network with rigid body dynamics by saying, if I hit this ball upwards with downwards with a force of say 2 newtons in this angle, it goes here, it goes here. After giving all that data, then we ask the neural network, okay, now if I want the ball to go here eventually, how should I hit the cue ball? And based on the experimental data, it guesses. And basically this is how humans learn billiards too. pool table. So after practicing few times, we know that okay, if I should reach there, I should go hit it in that direction with a bit of spin, or with less force as possible. And yeah, as you see in this box, it has finally learned how to, if it hits the ball in that direction, it will end up as close as possible to the target position, and that was their goal. And rigid body dynamics is learned by the billiards balls is learned by the neural network in this application again. This is the painting application I was telling. Sorry, the alphabet P of a mechanism. This is like a 6-arm robot, and it has 7-arm robot. How many motors does it have? It has around 5 to 6 motors. You should control the torque given to these motors. The neural network should, not the neural network. Here we are. This is a robot, and the policy of this robot is decided by the neural network, and that policy decides the torques given to these motors at any instant of time, such that it replicates the image on the left side. Say I have this human's face, it tries to mimic that human face to achieve maximum reward. It is trained already using many such examples and training for days and days and days on millions and millions of data points. Each data point is that an image and how it is drawing. And whenever it draws as close as possible to the input image, we give more reward, and eventually it starts mimicking the image to give as much reward as possible. So yeah, this is like the last slide. This is again a new field. It's not about rigid body motions. It's about solving differential equations. They're called physics informed neural networks, where neural networks are used. For example, a static stress analysis, you need to, for example, if you need static stress analysis of a submarine or a car or an aircraft, you might need many days, many hours, right? Now, what goes into a static stress analysis is something called a differential equation. I don't think you guys know differential equations. Yeah, there is something called a differential equation which guides the physics of the structure, and it gives the static solution from a static stress analysis. Now, in physics informed neural networks, we are going to train the neural network to learn these solutions. This is a fluid flow simulation. Fluid flows here, and we are going to give the output and input computed by traditional conventional techniques like finite volume method to the neural network. And eventually for differential equations which look relatively similar, for example, if you train the neural network for steel, now you are saying the component is made of aluminum, now solve the same differential equation for aluminum. As long as you give the material properties, because that's the only difference between these two applications, it would try to guess what the solution might look like as best as possible. So these are the results guessed by the neural network on the left side for the fluid flow, and the right side shows the errors as compared to the conventional mathematical exact solution, and the errors are not much. Blue indicates no errors, red indicates too much errors. As you see, there is no reds here, so there is it has learned pretty much. And yeah, this field is too new again, and it is not in any softwares yet. I hope it doesn't come into any softwares yet, because I would lose my job if this is into any softwares, because my thing is to actually make conventional algorithms. And if this comes up, maybe when I retire, hopefully it comes up when I retire, not now. So I just added this slide just in case you want to know in the future if you eventually pursue something in that direction. That's the end actually. There is a thank you slide though. So any question on any slide, I can elaborate on some slide. I know I went over time so much. I'm sorry. If you guys need any extra material on any of the slides I mentioned, this is a broad overview actually, nothing is deep. So if you have any particular interest on any of these slides, you can let me know and I can direct you towards the necessary material or how to start learning about that. I mean, yeah, as I said, all these slides are, all these fields are very advanced. So no questions? Okay, then yeah, that's what we have. Yeah, if you have any more questions, you can email me. I think you guys have my email address already. You can email me, or you can ask me if you need more references for any of the slides. If you want to learn more about any of the slides I showed, or how to start learning about some of the fields, because each of those slides requires so much of background math in it, and yeah, it's not high school math, unfortunately. So you might need to start learning if you want to learn any of these fields. So you can reach me out for that. Okay.
Thank you.
Thank you.
Yeah. So yeah, have a nice day then. Have a nice rest of the day and week. Yeah.
You too.
Wow. Thank you.